Thank you everyone to the afternoon session on Wednesday. So this afternoon we start Hisham Sati from NYU, and he's going to be talking about M theory and cohomotopy theory and hypothesis H. So please take it away, Hisham.
Great, thanks, Anthony. Thank you, and thanks to Yang and the other organizers for the invitation, and I hope we are able to meet in person soon. In this talk, I'm going to describe recent progress in on understanding of M theory using connections to mathematics, mainly homotopy theory and higher geometry. And so my talk is going to be a survey of many papers we've written with my collaborators listed here, Ur Schreiber, Domenico Fiorenza, Dan Grady, Vincent Brown-Ackmeyer, and on relating M theory to homotopy theory from various perspectives that I'm going to survey, and I'm going to try to keep my talk as non-technical as possible. And then towards the end, I'm going to touch upon recent progress and work that's going to show up soon with Sasha Voronov on related topics. So I'm going to start describing generally where we want fields in physics, and particularly in string theory, and then also M theory, where we want these fields to live. And then after that, I'm going to zoom in on M theory and describe how we want to describe the fields in that theory to the extent that we know what that theory is, using twisted cohomotopy. I'm going to say what that is, and I'm going to do things in steps. First, I'm going to look at the problem rationally over the rational numbers, differential forms if you like, and then integrally over the integers, and then differentially. Differentially really means differential refinement of a cohomology theory. It doesn't mean something analogous to one, although it's related, but it's in a way a combination of 1 and 2. You take 1 and 2 in a way, and then you get 3. But I'll explain all of that. And then once we have a description of what's known about M theory using homotopy theory, then we can say what are the consequences of some of this, and I'm going to describe some of them using in relation to brains and gauge theory as well, extending beyond the usual tools of M theory per se. All right, so here's a cartoon of how M theory relates to various concepts that are going to appear in this talk. So M theory relates to twisted cohomology, equivariant homotopy, parametrized homotopy, generalized cohomology, differential cohomology, higher geometry, supergeometry, and in a way, ultimately, in certain situations, depending on what background you take for M theory, you would have combinations of these, and maybe, and we do have instances where many of those, a good number of those, arise at the same time. So M theory is quite rich, as we perhaps know, but we're in a way parametrizing how rich it is by mapping to mathematics, which will help shed light on M theory itself, aside from the interesting connection to mathematics. All right, so where do fields live in general? So usually non-trivial physical entities such as fields, charges, you want them to live in cohomology because of the gauge structure, and then you want to have that cohomology be refined to a generalized cohomology to capture certain essential topological and bundle aspects of the underlying physics, let's say. You want it to be twisted to account for symmetries and automorphisms, and you want it to be differentially refined because you want to include geometric data such as connections, chain character forms, smooth structures, smooth representatives of maps, or all of them at once. And then one can introduce geometric data using differential forms that is, we want to retain the differential form representatives of underlying cohomology classes. So this is a cartoonish picture. It's not a math diagram. So you start with differential forms, and then you adjoin those differential forms to cohomology. You get a refinement, which is differential rational cohomology. It sounds trivial, but there are aspects of it that are not trivial. And then you take differential forms, you adjoin it to integral cohomology, you get a refinement, which is differential integral cohomology. And this is generically what one means when one talks about differential cohomology without further adjectives. And then you can adjoin differential forms to a generalized cohomology theory E, and then that leads to a refinement of that cohomology theory to a differential cohomology theory. So as you can see, the hats refer to differential refinement of the underlying topological theory. So this line here, these are homotopy invariant entities, and these lines here include geometric aspects as well. So what one has is an amalgam, in a way, of the underlying topological cohomology theory and the data of differential form, and this can be made precise through diagrams. So you got forms, and you've got a generalized cohomology, and they agree on DRAM cohomology, and then you have this pullback, if you like, which is the differential generalized cohomology theory. So this can be made mathematically precise, but I'm trying to be schematic and non-technical here. So that is another way of saying this is some sort of a twisted product or a fiber product. So you take cohomology, you combine with forms in a manner that makes them agree in the RAM, and that you've got yourself a differential cohomology theory. And differential generalized cohomology theories, you start with a generalized cohomology theory, and then you take smooth differential forms with values in the coefficients of the theory. Coefficients of the theory are the values of the theory at a point, and to a large extent, they determine the cohomology theory. And then one could look at the subset of closed forms with those coefficients, and then one can form the corresponding cohomology of the complex. And then a smooth extension, another name for a differential refinement is a smooth extension, is a contravariant functor from you want compact smooth manifolds to graded abelian groups. And this is just another way of writing this schematic diagram. Here it's written as a square. Here it's written as a triangle or a diamond, but it's the same data. You have an underlying cohomology theory. You have closed differential forms, and then these two match in the RAM, and and then this is the underlying differential cohomology theory. And there are maps that take you from this differential cohomology theory to closed forms and to the underlying topological theory. This is a stripping or a forgetful map, if you like. So that the full structure is having twisted, differential, and generalized at the same time. So jazzing up this picture that we have, want to add twists to all of this, you take the underlying picture and then you add twists everywhere. You can twist any one of these entities. You can twist integral cohomology, rational cohomology, cohomology theory, and then if you choose the twists compatibly with the differential forms and you do things properly, then you get twists by underlying differential cohomology classes of another differential cohomology. So this has quite a bit of structure in it. It's not just a class. You're not just twisting by a class. You're twisting by a whole, if you like, gerb with connections and all of that. And the main examples here are in string theory. So in type 1 or type 2 string theory, the monomorph fields live in twisted differential KO theory or K theory, respectively. And one establishes differential refinements of these various twisted cohomology theories, KO, K theory, and other theories as well that are relevant in this context. So this was a review, a perspective on where we want the fields to live in general, and zooming into string theory. But now one can go back to the main question and ask, well, what about M theory? That's the whole point. And then we want to do something analogous in the case of M theory. So M theory is supposed to live in some generalized cohomology theory, or the fields in it are supposed to live in a generalized cohomology theory. Well, first we need to identify what that generalized cohomology theory is. And then once we do that, then we want to go through a similar process as we're doing here, which is twist it, differentially refine it, and so on. So this is the second part here, which is describing the fields of M theory through, as you can see in the title here, we're identifying what that cohomology theory is going to be, which is cohomotopy, and we're going to contrast that with the default description, which is cohomology. Right, so just a quick review here about M theory through its low energy limit, 11-dimensional supergravity. You've got the basic entity that we're interested in is really that three form C3, which has a field strength G4 in the physics lingo. And you want to understand what C3 is supposed to mean mathematically, or G4. So C3 is some sort of a higher connection, and G4 is some sort of a higher curvature of some sort. And the equations of motion are these for G4. So we're not interested in metric aspects here. We're focusing on the topology. So at least you need to have differential forms. And you've got the Bianchi identity as well. And one can introduce what's called the duality symmetric formulation, or democratic formulation, where you have G7. So sometimes G7 is taken to be the Hodge dual of G4, and sometimes you take it as a, not sometimes in the same setting, two perspectives. So you can take the perspective that G7 is the Hodge dual of G4, or you can take G7 and G4 to be independent. And so now we'll go into contrast. So G4 is supposed to have an underlying cohomology class where G4 is closed, so you know it's going to have an associated cohomology class, but there are shifts and there are bells and whistles associated with it. But let's put these on the side for the moment and say G4 is simply gives rise to a cohomology class. So so a cohomology of Y with R coefficients is defined as homotopy classes of maps from your space Y, which in physics would be space-time, to some universal space. And in the case of cohomology, it's an Eilenberg-MacLane space. In that degree, that gives the degree of the cohomology with these coefficients, which gives you what coefficients you have, say integral. This R is supposed to be general, not real. And this, by definition, is cohomology in degree n of Y with coefficients in R. This is the default description. Now we want to say, now we want another description, and I'll explain why. Where you place this universal space, the Eilenberg-MacLane space, by the sphere in the same dimension with coefficients, and we'll explain what that means, coefficients in R. And then that, by definition, is co-homotopy. So it's more common to deal with homotopy groups, perhaps, where you have the index n, the degree below, but here when you have the degree above, it's called co-homotopy. And it's related to homotopy in somewhat similar way that cohomology and homology are related to each other, except that cohomology and homology are linear duals of, you know, if you pick the coefficients right, you have universal coefficients theorem and so on, module all of that. But here in homotopy, these are not linear duals. They're very far from being so. They're very nonlinear, and you've got a lot of nonlinear structure arising from this. And that's actually, in a way, what makes it useful in the description of the fields in M theory. So in comparing cohomotopy to cohomology, we look at the various flavors as in the setup earlier. So rationally, you have the rational force sphere versus the cohomology in degree 4, rational cohomology, and you have an integral version of this, and then you have a differential version of this, in the same way that you can have a differential refinement of usual cohomology. You can have a differential refinement of this cohomology theory. So cohomotopy is an example of a cohomology theory because it's a functor from spaces to a structure as we had here. Well, this is the smooth part, but it does fit into this structure here. So cohomology is what you have here, and cohomotopy would be an example of a generalized cohomology theory, which you're trying to differentially refine or twist or do both at the same time. Okay, so rationally, so first we'll go rationally, then integrally, then differentially. Rationally, the reason we want to talk about the force sphere that came out of the blue there, but one can see that it's not really out of the blue. If you have, well, after the fact, it's not out of the blue, that you have Eilenberg-MacLane space here of degree 4, and then the sphere of degree 4. The sphere, in fact, is what you think of when you think about naively how the sphere should behave. Then the answer to that would be the Eilenberg-MacLane space. The Eilenberg-MacLane space is your dream sphere. The sphere is actually packs a lot more than you naively or ideally wish for. But now we are in reality, and reality asks for the actual sphere, not the dream sphere, which is the Eilenberg-MacLane, the actual sphere, which is the force sphere. So one way of saying this is by looking at the equations of motion and the Bianchi identities. And we're trying to stare at equations and say, well, how much structure can we deduce out of looking at these equations? So we can extract differential, rational structure, differential form data, etc., or more refined structure. So G4, as indicated earlier, is some sort of a 2 degrees higher than your usual curvature of a bundle. So so in the hierarchy of geometric structures, a usual bundle, let's say, is indexed by 0, and then you can see that G4 will be described by a 2-gerb, and then it's twisted, ends up being twisted because there are shifts that I'm not talking about here. There are shifts arising from some fractions of the Pontryagin class that makes G4 minus that fraction to be integral rather than G4 itself. And these relate also to twisted string structures that are higher analogs of spin structures. So underlying these innocent equations is quite a bit of structure. So a priori, G4 should be described by a map from space-time to KZ4, Eilenberg-MacLane space, giving rise to integral degree 4 cohomology, again, modulo these shifts. And the differential refinement would correspond to differential cohomology. Universally, differential cohomology arises from looking at homotopy classes of maps from Y to a replacement of an Eilenberg-MacLane space, which knows about the underlying geometry, so which knows about connections, for instance, and there are constructions like that that allow, so we're able to describe these things by, this is with Fiorenza and with Urs and Domenico, and you replace, so KZ4 is the classifying, you apply the classifying functor B on KZ3. So KZ4 equals BKZ3, and then KZ3 is BKZ2, and so on. And KZ1 is U1. So you can see if you take this nabla away, B3 U1 is KZ4, and then the replacement of KZ4 with something that knows about geometry is this stack. I was trying to dance around the word, but yeah, let's say it's a moduli stack, and it homotopy classes maps from Y to this stacky maps correspond to these differential cohomology theories. But now the point, whether differential Eilenberg-MacLane or usual Eilenberg-MacLane, they have a product structure, the cup product, and a priori there's no information about trivialization. So we need a replacement of these spaces that knows about trivialization. So here, these equations, of course, traditionally they're read from left to right. I want to read them from right to left, at least the first one. I want the first one to be read as trivialization of the cup product of G4 with G4 at the level of cohomology. If you have G4 cup, G4 is 0, then at the level of differential forms, then G4 wedge G4 is D of something, and that thing is G7. So that's what I mean by trivialization of the cup product. So, so one can have twists. We want to talk about twists as well. So want to build a twist associated with G4. It's more common to have twists associated with the Nova-Schwarz field H3, which is a dimensional reduction of G4 down to 10 dimensions, down to type 2A string theory, and there's an analogous story for type 2B. And then one can have a de Rham complex associated with this, provided one interprets, one adjoins Grassmann algebra valued elements to this. And the main observation is that we have a twisted de Rham complex, provided that these elements satisfy this relation, and the forms themselves satisfy this relation. Of course, the second is the equation of motion, but the first is actually the M-theory gauge algebra. So it's the algebra that captures the gauge transformations of the C field and its dual. And then another main observation is that these equations here, these equations, equation of motion, the Bianchi identity, are captured by the Sullivan minimal model in rational homotopy theory of the force sphere. So if you look at the rationalization of the force sphere, and you look at the Sullivan minimal model of that, then it's exterior algebra on two generators, Y4, R7, satisfying these relations, which are exactly the equations of motion in this democratic formulation or duality symmetric formulation up to a factor of a half, which can be interpreted using homotopy entities as well, which is the Whitehead bracket associated with the quaternionic half vibration, allows for this factor of a half. One can scale these things anyway, but the factor of half particularly is actually very interesting in relation to the quaternionic half vibration, which eventually actually captures quite a bit of the structure of cocycles in M theory, because we've got S4, we're claiming S4 captures the dynamics, but then S7 over S4 captures further on top of that captures further aspects. And so the Sullivan model is sort of a cohomological counterpart in homotopy theory. And then there's a homological counterpart, which is the Quillen model associated with that. And then one can work it out in certain degrees. And it's a Lie algebra. And then it has a bracket, and the bracket in the Quillen model exactly captures the M-theory gauge algebra that we talked about here. So both the cohomological counterpart in homotopy theory and the homological counterpart in homotopy theory, they capture quite a bit of the initial dynamics in M-theory. But now this is the initial point. I want to go further. So the higher gauge fields in M-theory are cocycles in rational cohomotopy. And this was developed further, leading to differential cohomotopy. And the idea here is if you start with a generalized cohomology theory, there's a Chern character which lands in differential forms, and you can have a Sullivan model construction associated with that and rational homotopy theory. And associated with a generalized cohomology theory is an underlying full homotopy theory whose approximation or rationalization gives rise to this rational homotopy theory. And then one can work out models for various things that show up in M theory, Super-Minkowski, the Eilenberg-MacLane spaces, odd spheres, even spheres, extended spacetimes. I've been mainly dealing with the bosonic, excuse me, the bosonic aspects of the theory, but one can work out the fermionic aspects as well. And all these super co-cycles can be captured by super rational homotopy theory models. For instance, this M2 brane algebra that captures the extended space-time by the M2 super co-cycle. Okay, so some consequences is that the reduction of circle bundle allows us to capture rich aspects of the theory, and we are able to derive twisted K theory from M theory that way. Using cohomotopy in M theory, you do dimensional reduction on a circle, you get twisted K theory describing the normal fields together with the Navier-Schwarz field in 10 dimensions. And this actually works at the level of super co-cycles, meaning it's a first principles discussion. So one can look at the actual super co-cycles that show up in actual supergravity. Okay, and this is what I indicated earlier, that this can be done actually for fields of all degrees, including the co-cycles associated with the D6 brane, the D8 brane, so meaning the curvature or the field strength F8 and F10, which usually are not captured by a simple dimensional reduction from M theory, but using parametrized homotopy theory in this context, we are able to do so. And then next, I want to talk about integrally. So integrally, so we just saw that S4 rational is just the Eilenberg-MacLane it can be approximated. It's not exactly the Eilenberg. It can be approximated by the Eilenberg-MacLane space KQ4. Actually, there's a fibration, and then so H4 really coincides with pi4 with rational cohomotopy. But now, if we go beyond rational, what do we see? That's the point here. And one can do this stably and unstably, and one can do all sorts of flavors. This gets a bit technical here, so I'm not going to go too much into it. So one can have various flavors of refinements of this of these fields, depending on whether you're doing stable, unstable, etc. So this is hypothesis H, is that the C field is quantized in cohomotopy theory, even non-rationally. So this has a lot of effects, and I'm going to start looking at some of the effects of this. Let's see. Oops. All right, so one can lift the rational force sphere. Our starting point was the rational force sphere. All what these Solomon and Quillen models saw was the rational aspect of the force sphere. But now one can ask, is it really the actual force sphere eventually, as hypothesis HS? And one can pose this question systematically. So you have maps to the rational force sphere, and then the actual force sphere admits a map to that rational force sphere, and then you can try to lift. And of course, in doing this lifting, you are looking at integral information, torsion information, and so on. Analogous to that, one can actually contrast the description using cohomology versus the description using cohomotopy by comparing the maps, the one mapping to the Eilenberg-MacLane space, which is linear, to the one mapping to S4. And this actually can be done using what's called the Postnikov tower. of the force sphere. So doing that analysis then amounts to describing the C field in cohomotopy as corrections to describing it in cohomology, in integral cohomology. So you have the C field integral cohomology plus some non-trivial conditions given as obstructions give you what C field and cohomotopy is. So it's an enhancement, it's a refinement of the cohomology description as appropriate.
Hisham,
So,
you
yes.
under 10 minutes left.
Okay, thank you. I think I'll finish on time. I'll aim for that. So we'll consider M theory. The shifted C field is an integral cohomology class in degree 4, and then lifting that amounts to obstructions of this type. So you got some cohomology operation on that class describing the C field, and you have another cohomology operation. It's called the Steenrod square, which giving you obstructions. So as you can see, we need these to be 0, and now you have an equation involving the refinements of these fields is 0. So that's a condition on the theory. And then one can ask, well, is this a reasonable condition to have, or is it not a reasonable condition to have? And indeed, these end up being reasonable conditions to have, because that's what these are the natural refinements of the, for instance, number 2 is the natural integral refinement of an equation here in number 3. And then that number 1 here is amounts to canceling some anomalies that appear in the theory. Okay, so one can actually deduce some detailed aspects of this. For instance, one can get congruences about what prefactors show up in the action functional, in the topological action functional. One can actually get that from this analysis. And another aspect one gets is this Diaconescu-Moore-Witten anomaly, SQ3 and G4 is 0. One can get that obstruction as well. This actually leads eventually in another direction to elliptic cohomology, but here we're sticking with cohomotopy. So this cohomotopy theory can also be twisted. It can be twisted by something quite interesting, which is the J homomorphism, which is a map from the structure, tangential structure to automorphisms of the sphere, and we call this J-twisted cohomotopy theory. And so in hypothesis H, refined the C field for flux and semi-flux forms are subject to quantization in J-twisted cohomotopy cohomology theory. It's not a typo. Cohomotopy is a cohomology theory. In that they are the image of some Chern character. The way you see differential forms is by applying the Chern character to your cohomology theory, and there's a Chern character, non-abelian, albeit in the case of S4, from J-twisted cohomotopy theory. So doing this amounts to canceling all main anomalies that show up in the context of string theory, M theory. So for instance, it gives us the half integral flux quantization condition that I alluded to briefly earlier, but it's written down explicitly here. And the background charge, which involves this shift as well, this Diaconescu-Moore-Witten anomaly. W7 is a 7th integral C-flow in a class, which is SQ3 on the mod 2 reduction of this class, the Pontryagin class, and the integral equation of motion, and the M5 brane anomaly cancellation involving this inflow mechanism, the M2 brane tadpole cancellation, the number of M2 branes plus this quadratic background charge, giving you the one loop polynomial that has to be added to the action functional in M theory in order to cancel the anomalies. So all of these plus more can be extracted very naturally, canonically actually, from hypothesis H. So it's quite consistent. And there are other consequences for the the models of the M2 brain, the M5 brain, well, volume theories as well, that one can extract from this in a very natural way. Okay, and so one can describe, one can go in this differential cohomotopy theory systematically and extract differential form data. And the differential form data down here, they are exactly corresponding to what you expect from M theory. So everything is consistent. Now, differentially, so we have J-twisted cohomotopy and we have differential forms associated with it through this non-abelian Chern character. Differentially, we combine both, and we refine that earlier picture, which took Y to KZ4, lifted it to S4. Now we're differentially refining KZ4 to this stack, and then differentially refining S4 to differential S4. And S4, yeah, so it might look, again, somewhat strange that you have a force sphere and you're viewing it as a cohomology theory, but it's a cohomology theory in the way you map to it. Excuse me. And this requires a differential refinement of the Postnikov tower. So the Postnikov tower of S4 had many stages, say infinite number of stages, with the 0th stage being KZ4 at the bottom. Here, the differential force sphere is going to have infinite number of stages. A priori, of course, many of them are going to be trivial, with the base level being this stack here. And then one can work out what differential cohomotopy is. So earlier I said that S4 is approximated by KQ4, and I said it's a vibration. It's this vibration here. So what I said earlier was an approximation to this. So I can actually connect this cohomotopy to something equally deep and fundamental and canonical, which is the quaternionic half vibration. And these two go hand in hand. And then one can describe the structures that way. I think I want to move on here. One can have different descriptions, very explicit, of cohomotopy theory, and then one can describe the obstructions arising from differential cohomotopy, which generalize the obstructions that we saw earlier at the level of integral cohomology. Now that at the level of differential cohomology, and the cup product is replaced by the Deligne-Beilinson cup product, and the cohomology operations are replaced by differential cohomology operations. So there's a differential refinement at the level of higher bundles with connections to everything that I mentioned earlier. That's the point of this slide here. And now I want finally to talk about some consequences, further consequences, aside from fundamentally and canonically describing the fields in M theory itself. Now there are some consequences to this. So this is work with Oerschreiber. So there's a relation between differential refinement of cohomotopy and unordered configuration spaces of points. Once you establish that, which we did in that paper, then a lot of things fall into place. One can relate this to configurations of brains. Differential cohomotopy. So cohomotopy, differentially refine it. You get as a model configuration spaces of points. You take cohomology, you get weight systems on chord diagrams, which are very important in geometric topology. And through hypothesis H, going from cohomotopy theory, you get intersecting brains, and then the observables. Then the relation between weight systems and chord diagrams and intersecting brains is through observables, and this is meant to be a fiber product. Usually we write this on the left, but this, if we want to make it an actual math diagram, this would be a fiber product corresponding to those. So all of this, of course, has a mathematical description. This is just schematic, just to extract the main ingredients here. And then a lot of things fall into place and can be described very nicely all at once, actually. All these effects, M-theory observables and D6 intersecting D8 brain configurations, it involves parameterized homotopy theory as well, Cham pattern observables, string topology operations, multi-trace observables, matrix models, Hanani-Witten states, BLG observables, bulk Wilson loop observables, and so on. So all of that comes, if one wants to look at the geometric engineering aspect or the more down to gauge theory aspects, down to earth gauge theory aspects, then one can get quite a bit if one unpacks. So there's a lot involved in hypothesis H. So it describes the M-theory fields very nicely and explicitly and richly, and leads to a lot of consequences describing known things, and actually it predicts further things as well that we're working on. Lastly, this is the last slide, current work in progress. The paper is going to show up soon. It's relating cohomotopy to mysterious duality. So about 20 years ago, Iqbal Naich and Bafa related a reduction of M-theory on tori to Del Pezzo surfaces. Both are governed by root systems of the exceptional series. What we do with Sasha Voronov is bring in algebraic topology in the form of homotopy theory. So you've got this is CP2, of course. Del Pezzo surfaces arise from blowing up CP2 iteratively or one at a time under conditions. And you've got an outlier, which is P1 cross P1, which corresponds to type 2B. And we find a way of looking at all of this mysterious duality very naturally using the force sphere and its cyclification. So cyclification, it's some sort of a jazzed up loop space when you take, when you mod out by the action of the circle, and it amounts to dimensional reduction on a circle each time you take a loop space. So this cyclification captures the dimensional reduction on a circle, another circle, and so on. And these correspond to blowing up on one point, another point, blowing up on a line, P1, and so on. And so what we get a triality here, where we bring in algebraic topology. So you got algebraic geometry and physics through mysterious duality, although it is mysterious as the name indicates. That's why I have a dotted line here. And we have a solid line here because we know how to describe physics entities using algebraic topology solidly, as the theme of this talk has been. So this brings a solid line, and then this amounts to a purely mathematical duality then. It extends mysterious duality to a purely mathematical duality between algebraic geometry and algebraic topology, plus involving physics and a very detailed account of M-theory using Del Pezzo surfaces and generalizations of Del Pezzo surfaces. Great, thank you so much.
Thank you, Hisham, for the very thorough talk. Are there any questions?
I have a brief one. You might have mentioned this. Hi, this is George Minich. Interesting structure. I'm not sure I've absorbed all of it, but in the old closed string field theory of Barton-Zwiebach, homotopy Lie algebras, right, appear. Are there any relations between that structure in closed string field theory and what you're finding here in M-theory? The only relation I understand exists between string field theory and M-theory is if you go to light cone gauge, you can kind of match some computation in matrix theory and light cone string field theory, but nothing covariant. So, I mean, are there any relation between those structures and yours?
So the relation, not direct relation in the sense of like physics entities through math yet, although the underlying mathematics, L-infinity algebras, is what shows up all over the place in what I'm doing here, although I didn't mention it. Maybe I mentioned it once, but it's at the heart of what we're doing. So these models in homotopy theory, they involve L-infinity algebras, and the models, some of the models in generalized cohomology theories involve A infinity. It's the same underlying mathematical structures, if you like, but not a direct link. We're interested in looking at that, but no direct link, as in you derive one from the other, something to that effect. Not yet.
Okay. Thank you.
Thank you.
Great. So maybe because we're running a little late, if anyone else has any questions, they can contact Hisham offline. And let's thank him again for a great talk.
Thank you.